most sense, but what we're really at here is realizing that these two radii, this now big R prime radius and this now right on the lattice radius line, these two always, no matter where they are bisected by a line. In other words, equal angles here and here. This bisector of the dual radii has to be normal to the tangent vectors, that is the momentum at every point. Now, what's going on here? This is something we kind of skipped when we were talking about the weird coordinate systems. One of the weird coordinate system which was gotten by complex variable inverse sine is the hyperbolic elliptic ellipses and then hyperbolas that come in, and they are all very nicely orthogonal. So there, you imagine a hyperbola coming through here, going around the thing. That would be a coordinate system that was orthogonal, and the basic idea is that one of them depends on the difference. This one depends on the sum. If you're making an ellipse, you draw it by making the sum of these radii a constant. So you can reproduce that by just tacking a string here, and then running the pencil so the string is always taut. But when I wrote this paper, I wanted to make a calculator that would make the difference between these two the same. That meant you had to have a little pulley underneath the thing to reel out the string, giving each one equal amounts as you reeled. So that would give me a hyperbola around this focus. You follow me on that? So you can either make the sum constant and you go this way, or you can make the difference constant and you go perpendicular to this one. That's the main point. Okay, so that's a piece of geometry that's in what we're going to be doing here shortly. So no matter where you are on that thing, you're going to have two momentum circles that have Thales rectangle in them that define this business about P dot x and its relationship to the eccentricity vectors. Works for hyperbola as well. Okay, well, this is the next few pages show this construction. This is all you need to do to construct a general Coulombic orbit with ruler and compass. I mean ruler because sometimes you want to measure, but you can actually do it with rule and compass. So this is a ancient geometry technique that we're doing here. The idea is that you pick a launch point. Okay, you got this force thing. You blast off point, picked right there. And then you specify an elevation angle, and I like to use this angle, and you see why that is, I hope, by the end of this lecture. The angle that this thing makes with the radius. Okay, so gamma equals 0 means you're falling straight down. If you're thinking a quantum mechanical atomic orbital, you're in an S orbital if you're doing that. Okay, everything else has got some angular momentum, and it can be a P, D, F, it means angular momentum, 1, 2, 3, and so forth. But in this case, I just pick a direction. Okay, and I don't even yet specify how fast I want to go. I just pick a direction, and that's going to be have an orbit on it, have something that goes. Now the speed, the kinetic energy is going to be the important part of figuring out what orbit you get that starts with that momentum. And maybe if it has really a lot of momentum, it'll just go along that straight line. The heck with this thing, whether it was attractive or repulsive, doesn't make any difference. But most of them, if it's attractive, are going to bend down and do something like that, or like that. That's what we're going to be calculating. Okay? So the next step after this, and let's get all of these synced here so that we can talk about the details without squinting eyes too much. There's 3 steps that you need to do. 4 is pretty much the end of getting the focus locus. That's what you're after, and then you want to know where that focus is going to be. for certain situations. So that's just setting the stage, and then all you have to do is copy the gamma angle to get another line. That, remember we had a focus locus for the Rutherford scattering was just a vertical line. This one will depend on all of the settings that you made here for the launch angle and whatever latitude you want to launch from. And this particular thing is the focus locus because you just imagine what happens. The line R from the first focus, that's this one, okay, will reflect off of this. That is, this guy right here reflecting off of that should point. Basically, what I guess I'm saying is this guy and this guy. Back off so I can see the whole picture here. The line R from the first focus, that's this one, reflects off the line P, that's this guy right here, okay, bounces, bong, right, because this angle is equal to that. That's angle of incidence, angle of reflection, they're both gamma. Okay, so that's what I did when I copied this angle. I made a focus locus just by copying it right there and then drawing it all the way through. Okay, so somewhere on that line, depending on what else we say about this orbit, whether it's attractive or repulsive, how fast it is if it's attractive, we will be locating a focus somewhere, and then we'll draw the orbit given those two foci. That's the idea here. Okay. So, the next step is to copy the double angle, this thing. So we just copy it down here. Copy it right down here. Now basically what this is doing is making a line that is perpendicular to the momentum. So if you have another way to do that, fine, but that's probably the easiest way to do this in a general case, if you're playing with this as a geometrical exercise. So there's the focus locus, and there's this thing. And that turns out to be a kinetic energy ratio scale. That's it took me a while to discover this, but the basic idea is that you then mark it off in whatever scale you want to do. If you have a scaler already, you just draw parallel lines to make, say, 10 little tick marks. Here I'm doing it in quarter, half, 3/4, and 1, but these are all minus right here. In fact, all of them, all of the orbits that are attractive have R values. That's the ratio of kinetic energy to potential energy that is negative. And then all of the repulsive orbits, the Rutherford-like things, they're all somewhere on this side of the scale with positive values for this magic ratio. So we're used to sums of KE and PE, actually sum and difference, depending on whether it's Hamiltonian or Lagrangian, but here we use a ratio. This is not standard. This is weird. Okay, so so I say the next step is to tick it off so that you have actual marks here. Now this is the deal. The deal is that we are talking about a ratio of kinetic energy to potential energy, which is that thing. How did that come about? And I say, to be proved later, but have no fear. I'll do it in the center screen here, just to get it, and it'll be testing our link. This will take me ahead about 4 or 5 pages to the derivation. The derivation of that particular ratio is right here. There's the eccentricity vector. There's it written out as momentum times angular momentum. And angular momentum is an MVR, but it's multiplied by a sine of gamma. The gamma determines the lever, how close to directly in RU. And then the Km, of course, goes there. And this is being multiplied by a unit vector in the P cross L direction. That is perpendicular to both P and L. L's out of the screen, so this thing is perpendicular to P, and remember that's what we set that thing up with. So when you write all of that together, you get an mv squared over 2 times 2. There's no 2's there, but I put them in. And then the RO comes down to be a Coulomb potential at the bottom here. So there's your potential energy, there's your kinetic energy. That's the ratio that we're dealing with, and it's being multiplied by sine of gamma, 2 times the sine of gamma. So end of proof, okay? So let's go back real quickly here to page 67, which is where we started, and finish the construction. Both that one and this one. Now one of these gets finished with a hyperbola, that's this one. This one gets finished with an ellipse, because this ellipse has a nice negative point here with the ratio less than minus 1. Okay? Starting out here at 0, minus a quarter, minus a half, minus 3/4. Minus 1 is where this thing goes to. There's one point there, I should say, we imagine there's one point there which makes a parabola. But in any case, all of the points here cause an orbit that comes back. As soon as you get to that point, exactly to that point, you make that set of measures 0 called the parabola that has an eccentricity 1, exactly. And then anything down here with more, I should say less than minus 1, minus 2, minus 3, minus 4, all the way to infinity, those are all of the other hyperbolic orbits that have escaped the neighborhood of this particular force center. Okay? This particular force center. That's a nothing burger focus, right? Okay, so that's the basic idea. Now, over here, what I did was I went for the positive axis of this this R scale, this ratio scale. And all of these are positive. So every one of these is a hyperbola. A hyperbola that is repelled by the force center. Okay? So those are the things. Now, all of this is available on the, there's a hyperbola that's the same as this one, and there's a derivation. I'll just go through and extend the derivation with a particular example. Okay, and this particular one is a hyperbolic one. It is pointing to ratio of +1/2, and that goes to infinity. Now, this is the actual construction that this thing does. Now, what I should do here, there's a movie here, an embedded movie that shows how you play with this thing. Okay, you just go in there and set your initial conditions, and the epsilon vector will be made according to where you drag it. Okay, and then when you release it, you get an orbit for that particular eccentricity vector right there. And this is something TC built, and I didn't have at all anything like that with the old-fashioned animations that we have worked with so long. So the next thing we're going to do is something else that TC has really helped with, and I want to show that in just a minute here, but I think I'll go ahead and maybe just using this one and hoping the things go ahead and work the way they're supposed to. I'll do the Winch Detector, in real time here, I hope. Yes, so there it is. And you see what TC's also added is the momentum vector. And that's what we have to talk about next. That's why it does that, and show some better examples of the actual graphics that goes with that. So whenever you have something like this, you can just go in there and play with it, set your other focus. Takes a little bit of practice, and often you find yourself with your P vector off the scale, or in some part of the thing that doesn't make something you want. When you release it, it will usually make something that returns. In this case, I'm staying with the less than -1, and you resume when it stops to finish the orbit, if it can be finished. So that's what we're dealing with here. And obviously you very often want to erase the paths if you want to start over, or pause and erase the paths, and just pick any old point out here, and you know, build. You know, there's obviously going to be an ellipse that orbits around those 2 points, and I can bring this epsilon down to be very close, getting close here to the -1 case, but not quite there yet. It seems to be hanging on r equals 0. There we go. There's the epsilon right there. R of course will hang on there, but here I go to about a half. That's a pretty symmetric orbit. This is a pretty big orbit, and you can have them go, you know, way far away. You know, wait 5 minutes, and it comes back because we're within this region with our epsilon. This is the epsilon pointing to the actual r value, and that's the eccentricity for this particular orbit. Okay. All right. Let's pause all of this and go ahead with a little bit more algebra. Okay. Now this isn't the most elegant way. I'm pretty sure there will be better examples of this. There's the movie that tells you what the you know, how to sort of jerk these things around a little bit. So you can see you were running this yourself. Probably not quite used to how to make it. You know, it is a little tricky to
Still
run.
not. Yeah,
But
it's non-intuitive.
yeah. Okay. Let me go ahead here. Now I want to see what momentum does. I know what r does, and I got to get an equation for the polar angle in order to know what the momentum does. And so we're going to be working with phi dot and r dot using the equation of the ellipse, and that's the square of our usual radial equation right there. And then here's the derivative of it, and this is the thing that's constant. Phi dot obviously is L over the inertia mr squared, rotational inertia. And so you get an equation that looks like that can be matched to some things. The r dot that we have here works out fairly nicely. So we want to make use of some of those things using the square of our actual orbital equation. So we end up with a thing that looks like this. And we'll be getting something that gives us an x and a y coordinate equation. Here, of course, using the polar angle definition of it. But here's what the x dot and the y dot do. That is, if you're you know, tracking y dot, it's going to have a fairly complicated looking collection of sines and cosines, but they cancel really beautifully. Just cancels down to that. Let me go ahead and get all this up on this screen with the answer and the actual statement of the result. That is really quite remarkable, I think. This is certainly one of the more beautiful things in the Coulomb orbit world. It should be taken, made evident, shown in this. And that is that the, that the P traces a circle. There's the mk over L sine, there's the mk L over cosa, but an extra distance here, the eccentricity, whatever that is, and if it's not 0, it's got an off-center circle. Okay, so there's the algebra telling you that, but now let's just spend some time looking at that. Now, before I had TC's program completely working, I laboriously went through this, and I'll go through this very quickly on the center screen here. Just went through and did a geometrical construction of the momentum circle based on just the circle of the orbital. We imagine that this is where everything gets launched, and we're studying the various elliptical orbits, starting with this one, and there's that Fayetteville's rectangle construction of the p vector in scale. It's starting to pick up speed now. P's getting bigger when it reaches the top, our top, of the orbit. Okay, you see it has gotten many times longer than what it was started with, and here it is getting bigger and bigger and bigger. Okay, there's just a few steps here that do that, but it's, you know, this is not something, you know, this is a hobby. I shouldn't be making a big fuss about this, but it is, you know, really very beautiful. Now, it's probably time just to go ahead and show, and I'll get it on here in static form. It's already down. That's the end of the story right there. But here I have an animation link that I can make use of. Let me get it going here. And you see the little green thing there? That little green thing made that arc, that circle. Okay? So this really shows that structure of the momentum, making a circle. And it's a, you know, big leap there as it goes by the perigee. When it's at the apogee, the P is really small, and then it gets really huge because the perihelion is pretty small, and it's the proportional inverse of that. So I thought this, you know, this is something that you can really play with. In fact, I'd like to thank TC. I would, if you could give him a hand for building what is really a remarkable piece of geometry that has quantum mechanical significance as well. That's to be explored later on. Okay, so that is pretty much all I want to say about this kind of geometry. And I could, of course, go up here and see if I can make a really ridiculous one. I'm going to try to get the eccentricity vector to. And one of the things that is hard about this is getting the eccentricity vector on the other side than the one that you started on. You remember the trick to do that?
I usually have to stop and restart a few times, and then I get it back in alignment.
I'll just do one that's getting real close to R minus 1. That's pretty daring right there. See the R equal minus 1. And I'll pull off a little bit here and see if I can get it to.
Ooh, I believe you just snapped a picture.
I snapped a picture. That's what I did. Yes, I didn't want
I'll
that
search
picture
your features.
particularly well. Let's go back out of there and keep going here. I want to see that eccentricity vector. There we go. That's what I'm after. It's an eccentricity vector that's, you know, approaching minus 1. But let's not go too far. We'll be here all day waiting for it to come back. That one probably ought to behave pretty well.
It's still a little shallow.
Now it's on it. See, it's making a pretty big ellipse here, right? If I'd gone any further than this, we're already going to be here longer than I really want to be. It's going to come up here across the eccentricity axis. That's the axis of the conic section, which is an ellipse, pretty big ellipse. So it's really going slowly now. And the little green circle, you see the little green dot there making the circle. Now it's starting to fall again. Now we're falling, picking up a momentum. And also changing direction so that that little green dot stays on the circle. And we're just about where we started. There we come. Fall, 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 fall to the perigee. Bingo. Okay? So that's, you know, that's the kind of thing that just lets you do really easily. Okay. Here's the parameter system that works best, I think, for orbits, and I would use this if I was an astrophysicist because it shows it shows you a lot of things, and also it's a nice way to do perturbation theory of orbits, where you have other fields working on things. By the way, the R scale here is also drawn in this sequence, and that is done automatically
with TC's program. Okay, this business here is kind of neat. The R, KE over PE, and the ratio B squared over A squared are parameters that we've already talked about, but the fact that you can write them very easily in terms of R and gamma and get much simpler algebra, I think is worth noting. And that's kind of a summation of the whole idea right there. Okay, now normally I would stop the lecture at this point, but we've got a few. I think if I'm going to take a couple of minutes just to show you real quickly what it is we will leave as a study lecture. This is lecture 27 that I'm going to leave as a study lecture. And this is out of the textbook right here. This is an explosion right here that in the old program that I had back in the Stone Ages. Let me get this one ahead as well to this point. These are excerpts of the paper that came out describing a lot of this. But the basic idea here is, once again, a contact point, okay, occurs where you use from the center here, where you have the both foci employed, but one of the foci is actually here for the envelope. So the long distance to a focal point of the blue envelope has to be in line with the point that's contacting and the focus of the little orbit here. Okay, so there are two ellipses that are being married, so to speak. One of them using these two foci, that's the orbit itself, and then another pair that's this one and this one, building the thing that surrounds it and contacts it. In this case, only once, right there. So that's the thing to look for in these animations that I'm going to try to show that go with this. Perhaps the most spectacular one is this, and I hope that this machine is fast enough to get us through it. But I'm going to blow up a bomb right here in the Coulomb attraction center. Is here. It's attraction this time. So boom, okay, and roughly let's see, it says here number 200. That's perhaps a little much, but makes a continuous drawing. At first it's a circle expanding, but then this is attractive. So these guys are showing that that's attractive. And now the computer has to slow down to calculate a lot of stuff because we're getting close, and it's in order to maintain accuracy, it has to slow down. It does a little loop-de-loop. So now we got a bunch of the fragments coming or orbiting around that thing and coming back out in what looks pretty much like a circle, but an off-center one. And so all of these points here are going to pass the ones that are on the slow path to getting to the center of this orbit. Now, I've never seen that this happens anywhere. I mean, this is just really remarkable. This is one of those things you can do with geometry too, but I won't bore you with that. We're about halfway now. When these guys pass each other, and I'm going to do it just a couple more steps here. And while we're at it, we're drawing it with color for Lagrangian so that you could make a wave function out of this if you adjusted it properly. But this is pretty close to one. You can see that the coloring gradation maintains shape, so you're close to a quantum state. So now the loop-de-loop is going to close. Now finally these slow guys get to visit the fourth center. And remember, it blew up here, okay? So If you're out in space and you have a bunch of junk you want to blow up, and you blow it up, don't think it's gone. It's going to be back, all with a vengeance. And so here, this thing finishes the loop here. Now it's on the upside of recovery. And here it has to slow down because there's so many points that have to be tabulated, so the step size goes down. And it was bang, and now it's whatever bang is backwards. It's crunch. They all return to the point that they left. Just like that happened with a couple of examples that we showed with a harmonic oscillator. Okay, I think that's pretty much all I want to show. The other thing is solar wind and a comet. If it's an ideal situation with solar wind and no other funny stuff going on, a comet head is a hyperbola. That's kind of neat. Okay, and you can imagine astrophysical situations where the comet had more energy, on the average, to surround the repulsive. In this case, it's a repulsive place. And if you pick it just right, you can make the comet have a flat head. So it can be anything from what we saw before to this, to something that goes around. And you're making hyperbolas as envelopes now. Hyperbolic envelopes of hyperbolas are being made here in this particular case. Okay. Well, I think that's about it. That's the paper that goes with this thing. I hope you enjoyed this, and I hope you have a good Thanksgiving. This will interrupt your enjoyment of it with nightmares of being crushed by the exploding space bomb. Okay. And if you got the email, the problems are due after Thanksgiving on Monday. So.